Go to page 11 of your worksheet. November 16, P41. Now, what is meant by photoelectric emission? I mentioned that to you already. Photoelectric emission is when you talk about emission electrons from the surface of a metal when it's exposed to electromagnetic radiation at sufficiently high frequency. Okay. Yeah, maybe I need to talk a bit about your notes. Okay, whatever that I have explained just now in the separate screen, it covers this part of your notes. Okay, now the other part of your notes which I did not explain was this part all the way to here. Okay, I did not explain this part all the way to here. The reasoning is because I don't see any past year question related to this one, so I think I decided to skip it first. Okay, so this part I have actually skipped. I did not explain this part. I've only explained this part, and then after that I continue on from this part onwards all the way to I explain all the way to page 5, I think. Yeah, and then I explain all the way to page 5 of your notes. Okay, so you just make your own notes lah from in the notes there. Right, so just let me go back to this. Now, what is meant by photoelectric effect? Emission electrons on surface of metal when exposed to EM radiation at sufficiently high frequency. So, emission electrons from metal surface is one mark. Exposure to EM radiation at sufficiently high frequency, another mark. Okay, photoelectric emission, you need to have metal and you need to have EM radiation. Okay, so this part is clear. Now then after that, they tell you one wavelength of EM radiation emitted from a mercury vapor lamp is 436 nanometer. Calculate the energy of photon corresponding to this wavelength. So as I mentioned to you just now, E can be HF, E can also be HC over lambda. E is either HF or E can also be HC over lambda. So since they give you wavelength here, you might as well just use the equation with wavelength. Okay, so you get this. Planck constant 6.63 times 10 power minus 34 is taken from your data sheet. All right. Then you multiply with your speed of light, you divide by your wavelength, you get the answer as 4.56 times 10 power minus 19 joules. Okay, so that part is fine. Okay, now for part C, light from lamp in B is incident separately on the surfaces of cesium and tungsten metal. Data for work function energies of cesium and tungsten metal are given in figure 10.1. Work function energy, as I mentioned to you, this one is talking to you about phi, that symbol phi. The minimum energy of photon to remove electron from metal surface. Okay, keyword is minimum. If you're asked to define what is work function energy, you cannot omit this term. You must have the word minimum there. So calculate the threshold wavelength for photoelectric emission from cesium. So as I mentioned to you, HF naught will be equals to phi. or you can also say that HC over lambda naught is equals to phi. You actually don't need to derive from here to here, like you can just straight away use this if you wanted to. HC over lambda naught is equals to phi. So lambda naught, the threshold wavelength is HC over phi itself. So again, just sum in your values. Then you get your answer as in meter. Then you change to nanometer, because answer 1 is in nanometer. Okay, so that part is fine. You can use the nano is 10 power minus 9. This one you want to change to nano, there's an easy way from AS. Last time I mentioned 10 power minus 7 divided by 10 power minus 9. You get nanometer. You get this answer. I think it's easier you just divide by the conversion, by the prefix, you get the answer. Okay, so you get your answer is 888 nanometer. So this one is fine. Repeat the same calculation for tungsten. Threshold wavelength is Hc over phi. And you get your answer is 276 nanometer. Then from there, the question will ask you, use your answers in C to state and explain whether radiation from the mercury lamp of wavelength 436 nanometer will give rise to photoelectric emission from each of the metals. Now, the radiation from your mercury lamp has wavelength of 436 nanometer. For both of the metals that you're shining your EM radiation on, cesium and tungsten, you've already found out their threshold wavelength. The threshold wavelength here, as I mentioned, is the maximum wavelength for photoelectric emission to occur. Anything more than that, there will be no photoelectric emission. But anything less than that, you have photoelectric emission. So what you want to do now is you want to compare the values of your threshold wavelength and the wavelength of your EM radiation. Now, so for your case for cesium, threshold wavelength is 888 nanometer. I accidentally wrote that as 890 here. The wavelength of your photon, the one from mercury lamp, is 436. It's actually less than the threshold wavelength. So since it is less, you would have photoelectric emission. Okay. Now on the other hand, you compare for tungsten. Tungsten is at 276 nanometer, the threshold wavelength. Your wavelength of photon from the mercury lamp is 436, is more than the threshold wavelength, so there will be no photoelectric emission. Okay. So this one is a state and explain question. You need to explain why is there no photoelectric emission, why is there photoelectric emission by comparing the values of your wavelength with your threshold wavelength. Okay, so this part is okay. Right, so this part is done. If you're okay with that, you can go on to page 19 later on. So this part is fine. So threshold wavelength is one thing, threshold frequency is also another thing. I told you it is minimum frequency to cause photoelectric emission. Okay, so any frequency less than threshold frequency, you get emission. Any frequency more than threshold frequency, Sorry, there is a typo error here. If incident photon has frequency more than photoelectric effect does not occur. My mistake. If your incident photon has frequency more than threshold frequency, you do not have photoelectric emission. Hey, wait. If your wait, sorry, I got confused here. Threshold frequency is minimum frequency for photoelectric emission. So if your frequency is more than threshold frequency, you get photoelectric emission. If your frequency is less than threshold frequency, then you do not get emission. Yeah, that's correct. All right, sorry, my mistake. Okay, so go to page 19. Page 19, you would talk about the second part of your question, question A. June 17, P42. This one is be some okay, right. Now, briefly describe two phenomena associated with photoelectric effect that cannot be explained using wave theory of light. So as I mentioned to you, there were four main observations of photoelectric emission that cannot be explained if you assume that EM radiation is a wave, but can only be explained if you assume EM radiation as a particle called photons. So these four observations, please remember it. So just write any one of those four and you should be fine. You could say that there is minimum frequency of emission for electrons for metal surface. There's instantaneous emission of electrons. Maximum Ke or electrons emitted is independent of intensity, or maximum energy of electrons is dependent on frequency. Okay. So when you're talking about the energy part, please make sure you have the term maximum. This is important. Maximum Ke of electrons is independent of intensity. Maximum Ke of electron is dependent on frequency. Alright, so write any four of those and you should be fine. If this one is fine, then we go on to the next one. Okay, now the maximum energy Emax of electrons emitted from a metal surface when illuminated by light of wavelength lambda is given by this expression. Emax is hc 1 over lambda minus 1 over lambda naught, where h is Planck constant and c is the speed of light. Identify the symbol lambda naught. Lambda naught, as I mentioned to you, is actually your threshold wavelength, the maximum wavelength for photoelectric emission. Okay. So where did that equation come from? It actually came from this same thing here. Okay. I mean, I can derive it from here. Actually, I don't need to do it like that. I can just derive it here like this separately. Because I told you Hc over lambda is Ke max is 5 plus Ke max. So Ke max is actually Hc over lambda minus 5. But phi in itself, I told you, can be Hc over lambda naught. isn't it? So you get Hc over lambda minus Hc over lambda naught. You will get Hc 1 over lambda 1 over lambda naught. That's how you got this thing here. It means the same thing. Okay, it did not come for anything different. It still came from your photoelectric equation. Okay, so nothing here. This one is just the ones that is written in pencil is just another way of deriving the same thing, but I think this one is more straightforward for you. Okay. Now, then after that, they tell you the variation with 1 over lambda or Emax for the metal surface is actual. Then use the figure to determine magnitude of lambda naught. So as I mentioned to you, when you have this little diagram here, when you have this equation here, by right, you get this graph. Ke max over 1 over lambda is actually going to give you a straight line with negative y-intercept. And then this one is 1 over lambda naught. So the question now asks you to find out what is the magnitude of lambda naught here. So for the line that you have, you notice that they didn't extend it all the way. You're supposed to extend it all the way and then find out what is the intercept, the x-intercept. This part here is 1 over lambda naught. You notice the value is 2.2. So 1 over lambda naught is 2.2 times 10 power 6. Go and find out your lambda naught from there. Okay. So that one is fine. Then let me just move on. Okay, so if this one you're okay, then after that go on to the next question. They tell you use gradient to find out a value for the Planck constant h. Now, your gradient is actually going to be hc, isn't it? I mean, just now I did derive it for you just now. This one is Ke max. If I change to y goes to mx plus c, you notice that gradient is actually hc. Okay, because if I revert this now, if I try to revert this properly for you, Ke max is equals to hc 1 over lambda plus hc over lambda naught. So y equals to mx plus c. This one is m, this one is x, this one is y, this one is c. So gradient is hc. Okay, gradient here is hc. So find out your gradient, take 2 points and then equate it to hc and then find out your h directly. You should get this answer, 6.67 times 10 power minus 34. Okay, so that part should be done. Alright, so if this one is okay, then there's the other part here below. Okay, so if this one you are fine with that, then I move on. Now they tell you the metal surface in B is now oxidized. The photoelectric emission is still observed, but work function energy has now increased. On figure 10.1, draw a line to show the variation of 1 over lambda of Emax of the oxidized surface. Now, look at what the question is telling you. They tell you photoelectric emission is still observed, but work function energy is increased. When work function energy is increased, and the example I can give you is like maybe it was actually 1.2 eV, then it suddenly become maybe 1.8 eV. Now, in the form of a graph here, if originally it was 1.2, that would mean that it's here, negative 1.2 here, magnitude wise now, it will be at 1.2. If you suddenly become 1.8 eV, that would mean that you will be somewhere here, negative 1.8. Okay, so this part here would have to be shifted downwards because your magnitude has increased. So here, magnitude of y-intercept would increase. Okay, magnitude of y-intercept increase. Magnitude of negative, right there, but just write that. Magnitude of negative y-intercept increases. So you'll be here. Now, what about the gradient of the line, of the new line that represents this? You know that photoelectric emission is represented by this equation here. Okay, so it will still give you this same general shape. And since your work function is now increased, the magnitude of your y-intercept would increase. So the line is actually shifted downwards a little to represent a higher work function energy. But what can I say about the gradient here? You look at this one here, your gradient here is the product of two constants. H is a constant, C is a constant. Your gradient is constant, right? So for the case where your metal surface is now oxidized, it will follow the same equation. Because the gradient will still be Hc, the gradient actually did not change at all. So you will get a parallel line with same gradient. Okay, so this part here, work function energy is increased, magnitude of y-intercept increase. Then after that, you can also say that this one is number one. Number two, gradient of line is the same because gradient goes to Hc. That means it's constant. Okay, so since it follows photoelectric emission, you will say that Emax equals to Hc over lambda plus Hc over lambda naught still applies. So still same graph. Okay, so I think I better just highlight that. So the first thing you will say is this photoelectric emission? You see for photoelectric emission, that means this one still applies. You get the same graph. But then you see what function energy is increased, so magnitude of y-intercept increase. And then after that, you will also say that the gradient is still the same because the gradient is actually Hc. Okay, so all in all, with your metal surface being oxidized now, you expect to see this graph. This is the oxidized metal. This one is, say, the original metal. Okay, so the new line would be this one. So on your graph here, you want to draw, you just draw another line parallel to your existing one, but shifted towards the left, sorry, shifted towards the right. Because you see, in your case here, when this line is shifted downwards, it also has the effect of being shifted towards the right. So you just draw a line to the right, like this. Make sure your make sure it's drawn towards the right and it still maintains same gradient. So the easy thing for you to do is you pick 2 points on your graph, maybe this one and this one. If you see this one, you shift by say 6 units. The other point, you also make sure you shift by 6 units. So you have 1 point here, 1 point here. Then you just draw the straight line graph. Yeah, this part here just now I mentioned, because it's still photoelectric emission, so this equation still applies. This part I wrote still same graph, right? Not exactly same graph, still same graph shape. That one will be a more appropriate term to use. It will still be the same graph shape, not same graph in itself, but same graph shape. Okay. Right. Have a look at page 26. All right. Go to page 26. Page 26 is June 18. P42. Go to question 10. Describe photoelectric effect. We just went through that. It is the emission of electrons from a metal surface when it's exposed to electromagnetic radiation of sufficiently high frequency. Okay, so this one you just copy from the notes now. Okay. Now then go to part B. Data for work function energy phi of two metals is as shown. Light of wavelength 420 nanometer is incident on the surface of each of the metals. State-wise is measured by a photon. Now, a photon is just a packet of energy of EM radiation. Okay. Or you can say it's a quantum or discrete amount of energy of electromagnetic radiation, but I think it's better you just use the definition in pencil. 2 marks. Packet of energy, 1 mark. EM radiation, 1 mark. Okay, so this one is probably the shortest definition ever, but with so much marks allocated to it. Right, so photon is just a packet of energy of electromagnetic radiation. Then after that, calculate the energy of photon of the incident light. E is HF, or E is C over lambda. So energy of photon of incident light, they've already told you it is 420 nanometer. Just calculate it out. Kc over lambda, you get 4.74 times 10 power minus 19 joules. Okay. Then after that, you get this one. 5 was minimum energy required. Minimum energy of photon required to cause electric emission. So once you've done that, go to part 3. State whether photoelectric emission will occur from each of these metals. They've already given you the work function energy of sodium and zinc, which represents the energy of photon, the minimum energy of photon required to cause photoelectric emission. The energy of your photon itself is this one, the energy of the EM radiation, which is considered as your photon now. So the energy of your photon is 4.74 times 10 power minus 19. You have to make a comparison between this energy of photon and the work function energy. So logic will tell you that if the energy is more than the work function energy of photon is more than the work function energy of sodium, you're going to have photoelectric emission. If on the other hand, the energy of your photon is less than the work function energy of zinc, you're not going to have photoelectric emission, because this one means not enough energy. This one has more than enough energy. So this one, we could write something like this. More than enough energy. This one is insufficient energy. Okay. Right, so if this one is okay, then no issues here. You can go to page 5. Go to page 5 and have a look at that. Okay, so go to page 5. This one is November 15 P41. By reference to photoelectric effect, what is meant by threshold frequency? So what is threshold frequency? By now you should know it is actually that minimum frequency of EM radiation required to cause emission of electrons from a metal surface. Okay, so please be specific about that definition. If you just say minimum frequency required for photoelectric emission, that is pretty short. I think you won't probably get any marks for that because this is M1A1. You have to say minimum frequency of EM radiation. You have to specifically say that it is minimum frequency of EM radiation. This is important. You cannot just say minimum frequency to cause photoelectric emission. That one it won't give you any mark. Need to explain a bit further. Is the minimum frequency of EM radiation to cause emission of electrons from a surface. Okay, so this one is okay. Then this one here. If you go on to the next question. Okay, go on to part B. They tell you electrons are emitted from a metal surface when light of a particular wavelength is incident on the surface. Explain why the emitted electrons will have a range of KEs below a maximum value. So I kind of explained that to you just now already, where I talked to you about only electrons at the metal surface itself would have max KE. Only this part here would have max KE, and then here would be below max KE, right? Because as you go from here to here, energy required to remove electron from surface increase. In other words, more work needs to be done, so less energy or photon converted to KE. That was basically what I explained to you, right? Only electrons at the metal surface would have KE. But for electrons that are deep below the metal surface, they will be below your max KE. So the reasoning was because if you go deeper in, the energy required to remove electron from the surface will increase because more work needs to be done here. So if more work needs to be done here, you have less energy of photon that's converted to KE. So how do you put it in words here? You say this one. You say that only electrons at the metal surface are emitted with maximum KE. For electrons below metal surface, they are emitted with less than maximum KE because energy is required to bring them to the surface. That one relates to this diagram there here. So I think I also mentioned here max KE, least work to remove below max Ke, more work to remove in the way that I just mentioned this work to remove electron, more work to remove electron. Least work done. Okay, this one will just say least work done to remove electron. Least work done to remove electron, more work done to remove electron. Okay, so just copy that and you should be fine. Okay, so if this one is okay, then we go on to the next one. Now they tell you the wavelength of incident radiation is lambda, the variation of 1 over lambda or maximum K of Emax of electrons emitted from the metal surface is as shown in your diagram here. So you refer back to Einstein's photoelectric equation. HF is equals to Ke max plus phi, or Hc over lambda is equals to Ke max plus phi, such that Ke max is actually Hc over lambda minus phi. Okay. So now they're asking you, use your figure to determine without reference to the work function energy, the threshold frequency. Okay. So the graph that you have here is Emax versus 1 over lambda, which is actually Ke max over 1 over lambda here. Okay, you still expect to see the same graph where we tell you it is still a straight line graph like this. This one is Hc1 over lambda minus phi. This is Ke max. So you expect to see this graph. Okay. So you expect to see this graph. Okay, so that's what you need to do. Now they tell you with reference without reference to the work function energy, find out the threshold frequency F naught. Okay. Without reference to the work function energy, it means that they don't want you to find out from this. Hf naught is actually equals to phi. You can actually find out F naught from this equation also if you use the work function energy. But the question specifically tell you don't use something like that. Don't use work function energy here. Deduce it from the graph itself. Okay, so you're asked to deduce it from the graph itself. This one you know is negative phi. This one you know is 1 over lambda naught. And you know one thing, right? F naught would be actually equals to Hc over lambda naught. You can actually work out from there, but I think here there's another way of doing it. I'll just make use of that from there. Okay, now how do you go and find out the answer here? What is your F naught? The first thing you obviously need to do is you need to work out what is the threshold values. You find out what is the threshold wavelength here from here. So that one is usually occurring when the Ke max is 0. So at threshold frequency, I know E max is 0. The value of 1 over lambda naught here is actually 1.85 times 10 power 6. Again, they did not give you the full line. You have to extrapolate the line all the way to the x-intercept. And then you notice that this one here is actually 1 over lambda naught. Okay. So from 1 over lambda naught, how do you go and convert it to become how do you convert it to become F naught? You could use back this equation, V equals to F lambda. In this case, is C equals to F lambda. F is C C over lambda, you notice that this can be converted to this one, right? I mean, if I look at this one, F is C over lambda is the same as you saying C over 1 over lambda. So I just change this to threshold value. F naught is equals to C times 1 over lambda naught, which I already have in the first place. So this one is one way in which you can solve this question. If you didn't realize that, it's also fine. Eventually you get the same answer also. Actually, if you know that C is equals to HF naught is equals to HC over lambda naught. Sorry, yeah, HF naught is equals to HC over lambda naught. H and H cancel, you actually will still get back this same expression, but it actually doesn't matter. You will still get back same conclusion. Alright. So your F naught is 5.55 times 10 power 14. And then you have your answer. Then use your answer to calculate the work function energy. So now it's from here, then you start to use your work function for that relates to threshold frequency. It's here that you use HF naught equals to work function energy. Previously, just now they asked you don't use it, but here they ask you to calculate it out now, so you can use this. HF naught is equals to 5. So you know the value of your threshold frequency, you know the value of your Planck constant, you will get your energy. So you get it as 3.68 times 10 power minus 19 joules. Okay, so with that done, then you look at part B. They tell you cesium metal has work function energy of 2.2 times 10 power minus 19 joules. On the axis of the figure, sketch a graph to show the variation of 1 over lambda or Emax of cesium metal. It has some similarity with your previous question, but some slight difference. The question that you've done before this, where you needed to draw the graph, they told you work function energy has increased, but they never tell you the value. This current question is pretty specific in telling you what is your work function energy now. Okay, so when you draw this one here, it's not a matter of you drawing the same parallel graph shifted to one part anymore. You actually have to be a bit specific on where is the x-intercept here, because they've already given you the values here. It's different from your question just now. They didn't tell you the values of the work function energy, so even if you wanted to draw the graph, you just cannot work out where should your x-intercept be. You just choose a random value and just draw your graph. Here you cannot do the same thing. They've already told you specifically what is your work function energy, so you need to be specific on where is the intercept on your graph of your graph. So if you want to find the intercept of your graph, you can just use this. I want to find out what is 1 over lambda naught. Okay, now for your case here, just now, for that graph, for your original graph, Emax 1 over lambda, you know that, see, what metal is this? This one they never told you the metal, right? This one here, for the metal that you're testing, you do not know what is the metal. Let me just draw it out for you. You have this unknown metal here, right? From your question. And they tell you the work function is 3.68. So it's negative 3.68. Okay. Now your cesium metal has work function energy of 2.2 times 10 power minus 19. So you know that you still have photoelectric emission. You will still have the same graph shape, same gradient, same straight line. But this one here, the work function being 2.2 would mean that your line will need to be shifted outwards so that this one becomes negative 2.2. So you know that your graph needs to be shifted here. Still same gradient, because you can see from here, gradient is HC. So gradient won't have any difference yet because they are both still HC here. So it will be parallel line. But this one here, work function energy being lower, you need to shift the line towards the left a little. Okay. So here, when I say being specific here, I mean you need to know what is this value here. What is this value of 1 over lambda naught here? You need to find it out, which you can. If you know that HC over lambda naught is equals to 5, so 1 over lambda naught is actually equals to 5 divided by HC, which you get as 1.11 times 10 power 6 meter. Okay. So this part must be reflected on your graph. Okay, since the values are given, you need to show the values here. So what you do is your graph there, you find out 1.11 times power 6, which is actually here itself. This is your first point. You want to draw you want to draw a line parallel to your first one. You need to have 2 points. You already have your first point here, and you notice that it's shifted by I do not know how many units here. You calculate out from your own graph. Then you go and pick a second point. You pick a second point. If you see that from here to here you shift out by I do not know how many units, you go and look at another point, you shift by the same unit, but I also do not know how many units, and then you pick up that point. Then you have 1 point here, 1 point here. You use a ruler, draw a straight line. That one will give you your parallel line here. Okay, so please take that time to do it now. I'll give you a minute to do that. If you're done with that, then you can go on to page 7 or 9. Wait. Okay, the other question you can do is page 7. Okay, so I'm trying to do that. Oh, it's offset by 15 squares, 15 small squares. If you try to draw it at 1.11, you should see that it's offset by 15 small squares. So whatever point that you pick, second point that you pick, please make sure it's offset by 15 squares too. Then you have the 2 points to draw your straight line. If you have no issues with that, you can go to page 7. Page 7 is November 15, P43. Then this one will be question 8. Now for this part here, light of wavelength lambda is incident on metal surface having work function energy 5. Water electrons of maximum K Emax are emitted from the surface. State an equation relating phi Emax and lambda. So this one here, based on what they have, you should know that they're talking about the Einstein's photoelectric equation, where Hc over lambda is E max plus phi. Okay, use back the variables that the question has given you. Okay, I have a tendency to write things as Ke max. But here you do not write that same thing here because the question already defined for you is Emax. So don't go and change to Ke max like I usually write. Just use back Emax. Whatever the question gave you, please reuse it. Okay. So Hc over lambda is equals to Emax plus 5. Then the question asks you explain any other symbols you use. So whatever symbol that has not been defined in your question here, you need to tell them what it means. They already told you what is Emax. They already tell you work function energy. They already tell you lambda. The only thing they haven't told you is what is this and what is this. So you need to explain. H is Planck constant. C is the speed of EM radiation in vacuum. If you want to write the word in vacuum. Okay, so this part is fine. Okay, then if you're okay with that, then we go on to your next one. Now, variation of 1 over lambda of Emax is as shown by reference to your answer in 1. Explain why the gradient of the line does not depend on the metal surface. In a way, we've actually done something like this already. Why doesn't it depend on the metal surface? Because you will see that if you were to draw a graph of Emax versus 1 over lambda, your gradient is actually going to be Hc. Hc is the product of two constants. It's always going to be a constant, so it therefore does not depend on the metal surface. Your metal surface won't affect the value of C, right? Your metal surface won't also affect the value of H, right? So because those two are just constant, they are independent of anything, of everything. So metal surface definitely will not affect it. Yeah. So you have to explain what does the gradient actually represent. Gradient of the line is actually representing the product of H and C. If H and C are constants here, the gradient actually doesn't depend on the metal surface. It's not affected. Alright, so that part is fine. Then you go on to the second part where they tell you this. The work function energy of sodium is 2.28 eV. Find out the minimum wavelength lambda at which naught at which Emax is 0. They're actually asking you to find the threshold wavelength. Something is a bit wrong with this question. This one actually shouldn't be minimum. This one actually should be max because you're talking about threshold wavelength. But for some reason they put it as minimum. I do not know why. In your case here, when you want to talk about wavelength at which Emax is 0, you know this one is talking about threshold wavelength already. Okay, so work function energy of sodium is 2.28. Find out the wavelength at which Emax is 0. This one is talking about threshold wavelength. It's actually talking about maximum wavelength here. The minimum here, I do not know why it's here. It's very misleading. So you're talking about threshold wavelength. You know Hc over lambda naught is equal to 5. So sub in your values. 6.63 times 10 power minus 34 times 3 times 10 power 8 over lambda naught equals to 2.28 times 10 power 2.28 times 1.6 times 10 power minus 19 joules. Remember to convert your EV to joules. 1 EV is 1.6 times 10 power minus 19 joules. And you get your answer. Threshold wavelength is 5.45 times 10 power minus 7. Okay, so that much is okay. So let me just clear this one off. Then you go to page 8. This one I think is the last example that you guys can do. Go to page 8, which is your next page. There are some things here that you can actually just ignore because we've done that same question already, but let me just open it out for you. March 16, P42, question 11. Now, what is meant by threshold frequency? We just done that. The minimum frequency of EM radiation that can cause emission of electrons from a metal surface. So this one, I'll just keep it. You just copy the notes. You just copy from the notes when you have the time. Then B, electromagnetic radiation of wavelength lambda is incident on the metal surface. Electrons with maximum kinetic energy, Emax, are emitted. On figure 1.1, sketch the variation with 1 over lambda or Emax. So this one here, I've already done it a lot of times for you already just now. Also, you want to plot a graph of K Emax versus 1 over lambda, you need to make use of the photoelectric equation. Eventually, you get this form. And then you notice that it's supposed to be a straight line graph with negative y-intercept. So you're supposed to get this. Here you do not need to show all the way to here because they didn't give you this portion here. They didn't give you anything here, so you don't bother about that. You just show based on what they have given you. So you should get this line only. Okay, because by right, let me just see this. Just rewrite it. Emax 1 over lambda. By right, it should be this. Okay, negative 5, 1 over lambda naught. Okay, so just show for the part where they've written. Okay, if they just show you this part, you just draw only for the part that is shown. You don't need to draw this part. Okay, now let's get an equation relating the gradient of the graph with what you have drawn to Planck constant. Explain any other symbols you use. So by now you should already be very familiar that gradient here is actually hc. That's all. And then after that, they ask you to explain what other symbols have you used. They already defined for you Planck constant in the question. The only thing they've never told you is what is c. So c, you just need to tell them is the speed of light or speed of EM radiation in vacuum if you want to. Okay, so for part 3, they ask you to explain why for a particular wavelength of EM radiation, most of the electrons are emitted with kinetic energies less than the maximum value of Emax. This one we've actually done it already in some part. I think it is there was a question just now that we've done that relates to this. Let me see where it is. Yeah, the November 15 P41. We've actually done a similar question. Explain why electrons have a range of Ke values below a maximum value. This one is the same thing again. Explain why electrons are emitted with Ke's less than the max value. The answers are the same. The first 2 points are always the same. Electrons at surface are emitted with max Ke. For electrons below surface, energy is required to bring the electrons to the surface. Hence, the Ke will be less than the max value. Same answer also. So just copy this one. The one that I need you to do is part 4. Part 4 is a bit different. Okay, so have a look at part 4. This one you copy when you have the time and the answers are the same. Now, light of a particular wavelength is incident on a metal surface and gives rise to photoelectric current. The wavelength is reduced and then the intensity of light is kept constant. Explain the effect, if any, on the photoelectric current. Now, what is photoelectric current here? Photoelectric current here is this. If say for example, I have your metal surface here like this, and then I tell you I have the electrons. and I tell you that my photons are coming here, this one being my photons. So you know that under photoelectric emission, your electron will absorb the photons. If the energy of the photon is more than if the energy of the photon is sufficient, your electron will escape, and the balance of the energy of the photon will be converted to Ke. So for the part where your electrons absorbs energy of the photon, which is enough for it to escape, your electrons will escape. It could look something like this. Maybe this one will escape. Maybe this one will escape. This one will escape. This one here, the electrons that have escaped are called your photoelectrons. Okay, electrons that are emitted as a result of photoelectric emission. Electrons that are emitted as a result of photoelectric emission. These are what we call photoelectric emission. Now, when you say photoelectric current, it refers to this. Current is actually flow of charges, right? Isn't it? You understand that current is what makes up, current is made up of flow of charges. So when they ask you about photoelectric current is referring to this. Photoelectric current is referring to this. Okay, photoelectric current is basically flow of photoelectrons. That's what this one is talking to you about. All right, they tell you what happens here if you go and reduce the wavelength of your EM radiation while keeping the intensity constant. What happens to the photoelectric current? Photoelectric current here refers to the flow of the photoelectrons, or in other words, flow of emitted electrons, whichever you like. Okay. Okay. So what can you say about your photoelectric current now? So they tell you light over particle wavelength is incident on metal surface, giving rise to a photoelectric current, which is this one here. The wavelength of the light is reduced. The intensity of the light is kept constant. Still explain the effect, if any, on the photoelectric current. So now, your light is your photons. This one you know that light is photons already. Light is your EM radiation. EM radiation is photons. Okay. So energy of your photon is equals to hc over lambda. Okay. They told you specifically that your wavelength is reduced. Here they tell you your wavelength is reduced. From this equation, you'll be able to see that if wavelength is reduced, energy of your photon increases. This is the first relation that you can see here. Now, if you want to relate to intensity now, intensity, as I mentioned to you, is N times E over area times time, right? This one in itself is actually total energy of the photons. Total energy of the photons is actually the number of photons multiplied by energy of the photons. So it's Ne over AT. So this one I think I better write it out properly. This one is number of photons. This one is energy of photon. So they tell you intensity is kept constant. Okay, intensity is kept constant. That means I is constant, and you assume it's the same area. Area here obviously did not change, so I and A is constant. You eventually come to this conclusion, right? N over T is actually inversely proportional to E. isn't it? So this is the second relation that you need to know. N over T is inversely proportional to E. If here you already know that E is increasing, what would that do to N over T here? If E increases, N over T would drop. That means you have number of photons being less. You have less photons interacting with the electrons, the number of electrons emitted would also be less than. So if you have less electrons emitted, obviously your current will be less. Okay, so your answer looks like this. When wavelength is reduced, energy of your photon will increase, which is given by this. Since intensity is constant, there will be fewer photons per unit time, which is given by this. This in turn causes fewer electron emissions per unit time, therefore there is less current. Okay, so that part is okay. Now there will be some cases when you read from your textbook. I think I better just mention this. Did I? Yeah. When you're talking about intensity, this one is your answer already, but I need to talk to you about something else. Now, if you're talking about intensity, I is E total over area, sorry, E total over T times area is N times E over T times with A. This one here, usually we talk about intensity is for photons. You see, there's a thing that I notice people always get confused with. You have two things here, photons and electrons. Okay, be very specific about the terms you use. Photons and electrons here are not one and the same thing. They're two different things. When you're talking about intensity here, you're talking about the intensity of the photons. Okay. There are some cases also in some very old past year question, they ask you to calculate the photoelectric current. Now, photoelectric current, you will also give it symbol I, but this one is applied for electron. Okay, so this one here is for electrons. So in this case here, when you want to calculate current I is Q total divided by time. And then this one will be N times E over T. Okay. So this one here, when you're talking about N times E over T, this one is charge of electron. This one here, is number of electron. Wait, let me just erase all certain things here. I cannot. Okay. This one here talks about number of electrons. Okay, so this current I is for electrons. Okay, so be very careful about what you use. You might notice that some in the notes or in your textbooks, there's a symbol I, there's a symbol I, but please be very careful about what those symbol I's are talking about. Intensity is also represented by symbol I. Current is also represented by symbol I. So you will notice that sometimes the I has a different form of the equation. You need to look at what are they talking about. If it's talking about intensity of photon, then it's this one. Number of photons times energy of photon divided by time divided by area. But we're talking about the photoelectric current here refers to the electron, the flow of electrons. So if they ask you to calculate the current I, it is the total charge over time. So total charge here is number of electrons multiplied by charge of electron divided by time. So don't mistake this symbol and this symbol. Don't mistake this symbol and this symbol. They are talking about two different things. You need to look carefully at the context of the question. All right.